Imagine you're a student, staring at a page of handwritten notes. Maybe it's a complex diagram, a scribbled equation, or just a messy paragraph. Now, imagine an AI study tool that could instantly understand those notes, summarize them, or even generate practice questions tailored to your specific handwriting. This isn't science fiction, it's becoming reality. But how does a computer, which only understands numbers, look at a squiggly line and confidently say, "That's a 3"? What does it mean for a machine to recognize something as complex as a handwritten digit, let alone the nuances of your study material? In this video, we're going to peel back the layers of these incredible AI study tools. We'll explore the fundamental ideas that allow a computer to interpret your unique handwriting, understand the concepts you're learning, and ultimately, help you study smarter. It all starts with how a computer sees an image. For us, a handwritten 3 is a shape. For a computer, it's just a grid of numbers. Think of it like a tiny checkerboard. Each square on that board is A and LT, span style equals color yellow, and GT, pixel and LT/span and GT. If a pixel is dark, meaning part of the 3 is there, we can assign it a high number, say, 1. If it's light, meaning empty space, we assign it a low number, like 0. Or, more realistically, a shade of gray might be a number between 0 and 1. So, our handwritten 3 becomes a long list of numbers, one for each pixel. This list of numbers is what the computer actually sees. But how does it turn this list into a decision, like this is a 3? To make a decision, we need something that can weigh the importance of each of these pixel values. Imagine a simple light switch. If enough light hits a sensor, the switch flips on. Our first step towards AI recognition is similar, a simple decision-making unit, often called A and LT, span style equals color yellow, and GT, neuron and LT/span and GT. Each pixel from our 3 connects to this neuron. But not all pixels are equally important. The pixels that form the crucial curves of a 3 are more important than, say, a pixel in the corner of the image. This importance is captured by A and LT, span style equals color yellow, and GT, weight and LT/span and GT. Think of weights as knobs you can turn. A high weight means that pixel's value strongly influences the neuron's decision. A low weight means it has little influence. The neuron takes each pixel value, multiplies it by its corresponding weight, and then adds all these weighted values together. But why do we need to add something extra, a baseline level of activation, before making a decision? Imagine you need a certain amount of evidence to be convinced. This baseline is called the and LT, span style equals color yellow, and GT, bias and LT/span and GT. It's like an adjustable offset, making it easier or harder for the neuron to fire. So, the neuron calculates a total sum, all the and LT, span style equals color blue, and GT, input pixels and LT/span and GT, multiplied by their and LT, span style equals color green, and GT, weights and LT/span and GT, plus the and LT, span style equals color purple, and GT, bias and LT/span and GT. This gives us a single number. But we need a clear yes or no decision. This is where the and LT, span style equals color yellow, and GT, activation function and LT/span and GT, comes in. For simplicity, let's use A and LT, span style equals color yellow, and GT, step function and LT/span and GT. If the total sum exceeds a certain threshold, the neuron activates and outputs a 1. Otherwise, it outputs a 0. This is our neuron's simple decision. And LT, break time equals 2000 ms/NGT, so, one neuron can make one simple decision. But recognizing a 3 isn't just one decision, it's distinguishing it from a 0, a 1, a 2, and so on. We need more than one neuron. To recognize all 10 digits, 0 through 9, we'll have 10 output neurons. Each neuron will specialize in recognizing one digit. So, one neuron will try to detect a 0, another a 1, and so on, up to a 9. When we feed our handwritten 3 into this network, all 10 neurons will calculate their sums. The neuron that is most convinced that it's seeing its assigned digit will have the highest output. Ideally, the 3 neuron will output a high value, and the others will output low values. This combination of inputs, weights, biases, and activation functions is the core of a and LT, span style equals color yellow, and GT, neural network and LT/span and GT. The magic, however, is in how these and LT, span style equals color green, and GT, weights and LT/span and GT, and LT, span style equals color purple, and GT, biases and LT/span and GT, are determined. They aren't set by hand. The network and LT, span style equals color yellow, and GT, learns and LT/span and GT, them. We show the network thousands, even millions, of handwritten digits, telling it what the correct answer is for each. If it guesses wrong, we slightly adjust the and LT, span style equals color green, and GT, weights and LT/span and GT, and LT, span style equals color purple, and GT, biases and LT/span and GT, to make it more likely to guess correctly next time. This process, called and LT, span style equals color yellow, and GT, training and LT/span and GT, is how the network gets good at recognizing patterns. And LT, break time equals 2000 ms/NGT, but why do we need more complexity? What if the patterns are not simple, direct mappings from pixels to digits? What if we need to detect smaller, more abstract features first, like edges or curves, before combining them into a full digit? This is where and LT, span style equals color yellow, and GT, hidden layers and LT/span and GT, come in. Instead of directly connecting all input pixels to our final output neurons, we introduce intermediate layers of neurons. These hidden neurons don't directly output a digit, instead, they learn to detect specific features. Imagine the neurons in the first hidden layer learning to detect simple edges, a horizontal line, a vertical line, a diagonal line.